Okay, so let's get started. It's a pleasure to introduce today's speaker, Professor Seok Kim. Seok received his PhD from Seoul National University and held postdoctoral positions at the Korea Institute for Advanced Study and Imperial College London. Since 2009, he has been a professor at Seoul National University, where he works on microscopic descriptions of quantum gravity, holography, quantum physics of black holes. Today, he's going to talk to us about black hole pairs and information. And before I hand it over to him, there is a dinner sign-up list that's being circulated. So if you want to come for dinner, please sign up over there. And so without further ado, so please.
Thank you very much for the introduction, and thanks a lot for giving me the chance to speak at this lovely interview. So I'm a person working on theoretical physics, quantum theory, quantum gravity. And in this broader context, I began to study quite intensively some formal and theoretical aspects of black holes from 6-7 years ago. So I've been thinking about black holes from when I was very young, but it's quite recent I began to work on it actively. So I had to spend some time on what about black hole I should talk in front of all these expert audiences about black holes. And I decided to talk about one topic that I have been working on quite recently. It's about what's called the hairy black holes, the black holes which violate the no-hair theory. And I'm trying to convey to you various kinds of lessons that we can learn out of these classical and quantum studies of these exotic objects. So the theory of gravity, suitably set up, is known to satisfy what is the no-hair theory or no-hair conjecture, depending on the way you want to pose it. So for instance, consider Einstein's theory of general relativity. You couple it to certain matters. Let's say in the minimal setup, you couple it to electromagnetism to include the charged black holes within this theory. So the theorem says that stationary black hole, after the matters which collapse to form the black hole settles down, are characterized by a small set of parameters, the conserved charges, mass, charge, and spin, related to the symmetries of the system. And there are no more hairs remaining in the final solution, meaning that there are no more information available about the matters, complicated matters which collapse to form the solutions. And this kind of situation forms a lot of puzzles or paradoxes concerning the rich information of matters which used to be available before it collapsed and formed black holes. So it's related to it's one of the important reasons which poses a lot of interesting black hole information puzzles. Very interestingly, this theorem is sometimes often violated by including a different kind of matters and changing the settings and so on. And I'll try to explain that in detail, some details. And the violation of this theorem is also very interesting and leads us to consider the object called hairy black holes, carrying extra parameters except for these parameters that I've mentioned. For instance, they represent new interesting phases of matter, and there can be a lot of more interesting lessons if we can go out with it. So I today try to explain some novel examples of hairy black holes in a particular setup, which are of considerable interest to theoretical physicists. Then, after the middle of this talk, I'll try to explain to you how to make a quantum characterization of these black hole hairs that I explained to you earlier in this talk, and how to characterize the existence of hairs versus no hairs. Okay? And if time permits, I'll try to briefly close up mentioning some related information theory. So the no-hair theorem was developed in, I guess, in 1960s by various people in the theory that I've mentioned in the previous slide. And it's often violated. It's violated in various situations. For instance, it's violated whenever the technical assumptions used to establish this theorem has been lifted. Like you add more matters of more exotic sorts, you add more complicated, let's say, charged matters, non-abelian matters, Yang-Mills fields. I mean, there are many ways of violating it. If you're interested in studying gravity more theoretically, you can go to gravity in higher dimensions. You see Einstein gravity in higher dimension, space-time dimension higher than 4. It's also known there that the no-hair theorem is violated explicitly by having more exotic solutions. For instance, there are black hole-like solutions having ring-like event horizon rather than spherical, violating the theorem. And if you give to Einstein gravity some negative cosmological constant, it's very well known to be violated. And this is an example that I'll elaborate a bit more. Or it's also violated by having new symmetry structures in the theory, like more or less like 10 years ago. New asymptotic symmetry structures were found in the new horizon, and having more symmetry lead to more conserved quantities, which leads us to have soft hairs at the horizon, and so on. So there are many interesting directions in which the violation of the no-hair theorem give us some interesting physics. And today focus on what is called the black holes in this anti-distant space-time background. I also motivate that. It's a kind of setup which makes the studies of quantum and thermal physics of black hole better posed. And it makes certain studies of these black holes more better posed. I try to explain you the two things. A novel kind of black hole hairs in very simple black hole solutions in gravity and anti-distant space. And then I move on to quantum characterizations of the hairs of the black hole solutions I will be explaining to you. If there are questions, feel free to interrupt me. I believe I have contingency plan to wrap it up. So, so I hear there is a colloquium, so let me explain every technical things that I introduce in my talk, at least until a certain stage. So anti-distant space-time is a solution of Einstein's general relativity with negative cosmological constant. It's a space-time which looks like a saddle point, which has negative cosmological constant, which has negative curvature. And it plays a role of a gravitational box gravity. It's very hard to, So the metric of this anti-distant space-time in certain slides is given in this form. It has a radial direction, it has a time evolution direction. Unlike the Minkowski space-time, it has a center. It has a preferred center, which I take to be rho equal to 0. Okay. And this space-time wants to abstract all the massive matters, massive particles and massive black holes and so on. It wants to put all the matters towards the center of this space-time. Okay. So it's playing the role of a natural and gravitationally consistent box in which you can confine every massive object. Okay. And this makes many questions of gravity better posed, including black holes. Actually, the people who first studied this, who studied these black holes in this anti-distant background were Stephen Hawking and Don Page in the 1980s. And their motivation was to better understand the thermodynamics of black holes by putting it effectively in a confining box. There's another reason why we are interested in studying gravity in this gravitational box or the anti-distant space. We know a better description of quantum gravitational system in this space-time using an advanced concept called ADS-CFT duality or holography, meaning that we know a consistent quantum mechanical description of this gravity using some reasonably well-known quantum system living at the boundary line, which looks like QCD or Yang-Mills theory, so on, having large number of gluons. So QCD has SU2 asymmetry and gluons, but the quantum distribution of gravity inside this gravitational box can be described by QCD or Yang-Mills-like theory, having many number of gluons, largely. So this boundary quantum system describes the gravity inside holographically, which makes you to access some quantum questions better posed, and you can construct them more. With this in mind, I've tried to study some aspects of black holes within this gravitational box. So I'm going to explain to you the appearance of hairy black holes, of certain black holes put in this gravitational box. I'm going to consider rotating black holes in ADS, which is often called the Kerr antidistal black holes, is one of the simplest gravitational solutions you get out of the Einstein gravity with negative constants. Motivate the necessity of the hairy black holes, I consider the instability of these black holes first in this slide. The easiest way to argue that there should exist more novel, exotic kind of hairy black holes is to perturb the black hole. Not all hairy black holes can be obtained by perturbing on hairy black holes, but some black holes can. Some hairy black holes can. If a perturbed black hole turns out to be unstable, it's going to roll down to more exotic configurations, developing matter hairs outside the event horizon. So we study perturbing these rotating black holes in ADS. And the rotating black holes are known to have very novel region called the ergosphere. It's a region in which exists except right outside the event horizon. It's a region where the space-time itself is heavily dragged by the strong gravitational rotation of this rotating black hole. And taking advantage of this ergo region, ergosphere, one can develop various interesting process in which you can extract energy out of the black hole. And that process exists no matter whether the core black hole is in ADS spacetime or in flat spacetime. With ergo region, you can develop such a process. Depending on the setup, you'll either call it Penrose process in the particle picture or superradiance in the wave picture. In the superradiance picture, this process can be summarized as you send in an influx of current in the form of waves and making some dynamics in this ergo region. The outcoming, you can have the outcoming amplitude of the flux to be larger than the incoming amplitude that you have sent in, giving you effectively a way of extracting out larger energy than you have put in the black hole. So we call this superradiance. In a symptotically flat curved black hole, this is the response, a novel response of a rotating black hole to the influx that you have sent in. You sent in some flux, it may spit out some more energies and angular momentum energies. But if you consider the same phenomena in anti-resistor space, remember this is a gravitational box, it leads to genuine instability. Okay? So you consider a small perturbation given to the black hole, very faint, so it's a very small perturbation. So it has a small influx of energy into it, ergo region. And it can spit out some larger amplitude due to the superradiant process, still very small, but due to the presence of a wall, it can reflect back because the wall is attracting every energy, objects carrying energy to the center. And this process can repeat, keep amplifying and leading to a generic instability. You put an infinitesimal, very small deformation by perturbing the solution, you get a finite difference. So the stability means that if you perturb it, it wants to go back. Instability means that if you slightly perturb it, it deviates from the original solution by a finite amount. So it means a genuine instability in anti-resistor space. So this simple solution in certain situations by repeated superradiance and the reflection develops unstable directions. And 21 years ago, Victor Cardoso and Oscar Diaz have in fact found a large number, actually an infinite number of these unstable perturbations if the black hole is rotating sufficiently fast. The black hole horizon's angular velocity is sufficiently fast with respect to this boundary. So this is a superradiant instability.
So how important is the ADS here? Like if I just take a regular black hole and put it in a box with reflecting boundary conditions, can I get these things?
Morally, I think we can get the same thing. I mean, how consistent can it be on the gravitational setup? I'm not sure. I mean, actually, the motivation of Hawking and Page was to do it consistently within gravity. Okay. So if you can do it consistently by putting a box by hand, I think similar phenomena will follow. Yeah.
I think it was like Press and Early, they had the black hole bombs. And that was exactly a rotating black hole in Press space. In a box.
I think so. Do you remember when that was?
It was a really long time ago.
Much longer than this, I guess, right?
Way before that.
I see.
Earlier.
Probably before Hawking and Page, or around that time.
What was that?
83.
Yeah, maybe around there.
Okay, okay. Probably the same thing, probably the same thing. Yeah, but I just vaguely remember what you said, so, yeah.
Was the press in the early 70s,
Early seven,
the black hole bomb.
and early too. But anyway,
Mikulski and
Probably, the different, I guess you're right. I mean, I should look it up. Yeah.
The existence of the instability depends on the boundary conditions on it.
Yes, yes, yes. This reflection of these modes and so on, yes. So this leads to some instability. Any of that. So you found lots of instabilities of a very simple looking solution. It means that it's an unstable solution of Einstein equation, and it raises the question of what's the endpoint solution. After this unstable mode condenses, it will develop some non-trivial energy and angular momentum profile outside the event point. What's the final rotating hairy black hole solutions out of this condensation of this unstable question? If you remind yourself or learn the black hole thermodynamics of this black hole, you can broaden your viewpoint about this phenomenon. I've so far explained this instability as a dynamical phenomenon, but you can have an alternative or complementary thermodynamic view of it. So the black hole thermodynamics itself is also a subject with quite long histories, decades. And it started by what's called the first law, and among others, first and second law of black hole thermodynamics, which started their life, I understand, as an analog thermodynamic behavior of classical gravitational solution. So the first law says that black holes, for instance, can absorb energy in the form of mass, mc squared, in various forms. You know, it can absorb things in the form of a work, in the form of a chemical work, or and finally it can absorb energies in the form which is analogous to heat. If you formally identify the area and the surface gravity as entropy and temperature, and this analog entropy area is shown to be increasing the time evolution, never decreasing. And it became more serious topic of discussion after it was found by Hawking and Beckett Hawking said that the black hole should make some thermal radiation, giving a real temperature to it. And after the work, also the afterwork of Andy and Kuhlmann, that the analog entropy given by area is the actual entropy that physicists discuss in statistical physics. Namely, quantum and statistical physicists interpret entropy as counting the number of possible quantum states at given conserved quantities. And this is exactly the case in the exam. So what this black hole thermodynamics says is that we should really understand black holes among many possible viewpoints as representing an ensemble of states or collection of states at a fixed set of conserved quantities like energy or the mass, angular momentum, charge, and so on. In this thermodynamic point of view, the interpretation of the instability at over-rotating black holes is somewhat easier to understand. So we consider the matters that these unstable black holes can emit. They carry angular momentum as well on top of energy. Energy and angular momentum can be emitted by this process. Giving some angular momentum to a matter also has an energy cost. It turns out to give a minimum of the energy cost that a matter should have once given angular momentum. It's somewhat like, so it's somewhat like if a particle has a linear momentum, it also requires energy through various dispersion relations. And the minimal energy required for given momentum is reached by massless particle, where E is roughly p times the velocity of light. Angular momentum does similar things for the matters rotating in this gravitational ADS box. And the lower bound turns out to be roughly J plus 1 or something, but I'm going to ignore these small details for large charges. And it's saturated by some states rotating in empty space-time, like E equal to P. Using this fact, one can really see from this first law and second law of black hole thermodynamics to draw out the following conclusion. Consider a black hole which is over-rotating. Its angular velocity is naturally identified as the chemical potential for the angular momentum. If it's over-rotating larger than 1 or larger than the inverse of the ADS box, it can increase its entropy. The black hole can increase its entropy by emitting such matters, saturating this bound, carrying energy and angular momentum. Using this first law, you can see that. So the increase of entropy, forget about charge now, is related to increase of change of energy and change of angular momentum, which is given this way. But you're emitting this critical matter, saturating the bound. So it's the change of angular momentum of the black hole by emitting such matters times 1 minus omega, which is negative. So both are negative, so it becomes positive. It means that it can increase the entropy by emitting such rotating matters if it's over-rotating. Okay. So it gives an alternative thermodynamic interpretation. Black holes as a thermodynamic object want to increase the entropy. That's the reason why it wants to emit. Okay. Similar conclusion can be made for charged black holes, just as a side comment. If it's overcharged, it has too large electric chemical potential, it can emit the charged matters, increase its entropy. Yes.
How is this argument in the middle? Like, why does it go through? How does it feel in like flat space?
Yeah. Probably it's a weak argument. Probably it's a weak argument. Yeah, probably it's a weak. I mean, in flat space, many things goes much weird, even from this dynamic perspective. I told you that this omega has to be larger than the inverse size of the box. You know, if you take the box size to be infinity, you'll get into the asymptotic black hole, it's getting 0. So it means that any rotating black hole can have similar phenomena. I mean, and that's wrong in the dynamic case, because it doesn't have the reflection process. If you take the limit, box gets larger, it takes really, really long. I mean, if you want to approximate, in some sense, it's true that you can approximate small black holes placed in large ADS as approximately the flat black holes. But concerning this dynamical process, it takes a real long time to bounce back. So for a certain range of time, smaller than ADS scale, you can ignore this effect. So it's a matter of time scale. Thermodynamics, I have to think of it. Yes. But I believe similar kind of caveat might exist.
Yeah, no, I mean, the thermodynamics argument still holds the same way. Like, Solovy's original argument is you don't even require a black hole or boundary conditions, the instability disappears. You have superradiant amplification, but you don't get any instability unless
it's just you send it a flux once and it's a one-time event. Yeah. I think that's fair. Yeah. The process is not repeating. I think that's the thing. Thank you.
In the second of the omega greater than 1.
Yeah.
Is that, did you set LADS to be 1? Or
Yes. Sorry for not mentioning that. So in all the discussion I've been mentioning, there is one intrinsic length scale in my game, so which is a size of the box. I set this to be 1 and measure all the dimensional parameters in reference to this ADS scale.
Okay. So that's not like the curved black hole that has a naked singularity.
No.
So that's the okay.
It's not this one. Yes. So having said all these alternative viewpoints, dynamical and thermodynamical viewpoint, let me explain what's the situation in the solution space of curved black holes. So curved black holes have 2 parameters, mass or energy and angular momentum. I scale it with the Newton constant. So I plot the fate of this curved black hole solution in ADS in the 2-dimensional parameter space. There are 3 regions which I like to emphasize to you. One is the red region. Okay, it carries large enough angular momentum per given large enough energy per given angular momentum, and it's the region where the black hole is stable. It's the region where black hole is under rotating in reference to black ADS size, and it's stable, no instability issue, and no reason to particularly doubt there should be hairy black holes in this region. It's bounded by this red line where omega is 1. So it's marginally stable there. And this red line will play an important role in the talk. If you move down to lower energies at given J, you run into a blue region where omega is larger than 1. So that's where unstable black holes exist. It goes all the way down to the 0 temperature extremal curve black hole in ADS. All the way down to the extremal curve black hole, it's unstable under this superradial instability. So this was the region that I've been mentioning in the previous slides. I should also emphasize a third region, the white region between this green and blue line. In the white region, no curved black holes exist. But I recall a kinematic bound that I have been mentioning in the previous talk. I told you that putting angular momentum to object has an energy cost, and the lower bound is J. And that applies to black hole as well. I mean, that applies to every kind of massive object, including black hole. Okay? It just says that having angular momentum, nothing can exist below this line, but it can be kinematically allowed in the line of region above it. So in this white region, one might have had some black hole solution in this region, but in the curved black hole space, one happens not to have it. Okay? So that raises another question. Does the black hole solution really don't exist in this region? In which case we can thermodynamically interpret that the quantum gravity system in this charge regime doesn't really have macroscopic entities. In this case, this is kind of the second point I'd like to make. The first question is, in the unstable region, what's the hairy black hole? The second question is, in this white region, are there really no black holes, or are there some? Okay. The two questions are turns out to be closely related, so I'll discuss these two questions together. And it has been quite a puzzling question for more than 10 years by now, for some good reason I like to explain. So just to briefly introduce to you some developments about these hairy black hole solutions in this gravitational box. I should admit that I really have weakness in older literatures. This was the time when I was a postdoc, which everything after this time I vividly remember. Something in the 90s, 80s, 70s. Please bear with me if but I really remember, I think most of the things in the 21st century. So as long as we remember, along the way, I prefer to think the real important progress has been happening from 2008, from a work by Stephen Gopser. He has been considering some hairy black holes with planar horizon. Normally black holes have spherical horizon. It's a very weird black hole object which has just non-compact planar horizon. It makes some studies simpler. He found some progress about the hairy black holes with planar horizon, which is overcharged. And he found some hairy black hole configuration, approximately, analytically, and numerically, and so on. Similar progress has been happened afterwards with spherical horizon, the charged black hole, in ADS gravitational theory, plus electromagnetism, plus some charged methods, which want to condense. But the progress on rotating black holes was surprisingly slow. It has been considered by real experts on general relativity for more than 20 years. Some people found, after heroic efforts, some numerical hairy black hole solutions. But the problem is that there are so many unstable modes in curved black hole. Okay? Actually, there are infinitely many unstable modes. So even after one finds some hairy black hole configuration, having one unstable mode condensed, it's again unstable under the condensation of more unstable modes. So the final endpoint seems to be extremely difficult to find. Okay? So people keep finding hairy black hole solutions with larger entropy at same charge than the current ADS black hole, but still that's unstable, and it goes on. And very sophisticated works were going on until these papers, and yes, and that's part of the reason why studying this rotating black holes hairy burden is much more difficult. So I was reminded of this question by my collaborator Minala, I think around 2019, doing some completely different chats, and got to make a suggestion for the endpoint of this solution, which general relativity people, I feel actually very dislikes. So let me explain what that is here. Okay. Whenever you'll soon realize why general relativity people will dislike that. But let me try to explain that. So what you expect about these unstable black holes is start with black holes which are over-rotating. It will emit various kinds of particles outside the event horizon until angular momentums are emitted. The omega is yes, please.
So I thought up till now everything was classical, wasn't it?
Yes, yes.
What do you mean by commit? Is that fucking right?
Super radiance, so classical radiation. The classical radiation somehow I'm going to treat quantum mechanical way. Yeah. But emitting, okay, let me say, okay, this was a wave. I meant wave. I meant wave. Wave. I just said it's particle because that's the word I should have used in a colloquium, but it's wave. Yeah. And I'm gonna, yeah. At some stage, I'm gonna treat these waves as quantum mechanical wave functions during the, but it starts to state as a wave. Yeah.
But this is it's a classical question, correct?
Yeah. I slightly changed it to a quantum problem and phrase the solution, but it will start its space with a problem. So classical GR problem still there. Probably it'll be clear after a few minutes, but we changed the question slightly into a quantum mode and suggest a solution for that.
And that'll come back to a classical solution, or is the classical puzzle still there?
We have a suggestion for what will happen in the classical solution, but it's a bold suggestion. Nobody have elaborated on it, so we have a suggestion for what will happen in the classical solution, but yeah. Maybe if it's unclear, you can probably come back.
So just getting a bit nosy what's going to happen, but
Okay, sorry.
so you mentioned that you're going to treat it quantum mechanically.
Yeah,
Is there
actually somewhere here. Yeah.
Justification that quantum mechanical phenomena, really H bar is going to be important in this process?
Yeah.
Just move your mouse or something. Maybe it went to sleep.
Why don't you answer the question while I try to do this?
It's just
Thinking this one might have turned off. No, it is.
Is it connected to the wall? No, the cable.
The cable.
System to the wall. Installation.
Yeah.
You have an HDMI port on your laptop.
Yeah.
Let's do that.
Make sure it's plugged in.
Hope some of you can judge. Or I proceed. Can we hopefully come back to that sentence? Yeah. So think that. Various waves will be emitted, which are waves for the particle modes. And it will be emitted until the black hole over rotation slightly gradually slows down to omega equals close to 1 when it will be no longer unstable. So having this kind of picture in mind in foresight, we study black holes and emitted particles or waves on the verge of instability when omega is very close to 1, slightly smaller. So there's no instability issue, but very close to 1. At omega very close to 1, I want to study the thermodynamics of these emitted particles or waves, particles which are obtained by quantizing these waves. Okay? I want to study thermodynamics. And you can show, and I think probably this is the step where the quantum aspects are just searing in, that you can show by various calculations that the particle thermodynamics at angular velocity close to 1 is dominantly determined by the matter modes which are saturating this equal to J bound. Furthermore, at very large J. There are various ways of seeing it, but to show this using minimal amount of formula, we consider the thermal occupation number of a particle, the quantized particles of the waves, at given energy and angular momentum. Okay. It's given by the following number, either Fermi-Dirac distribution or the Bose-Einstein distribution for definite mode. To consider this equal to J mode, it's roughly given by this. So Fugacity factor multiplying Fugacity factor weighted by J. And normally, had omega not been close to 1, this Fugacity factor is smaller than 1. It provides a quick suppression of the modes carrying large angular momentum and energy. But this is a very extreme situation, so that the occupation number doesn't die off quickly, even for reasonably large J, because this Fugacity factor is almost close to 1. So unless J becomes extremely large, inversely proportional to this small 1 minus omega, the occupation number will not be suppressed. This gives an indication that the particle, the wave modes with large J will proliferate thermodynamically when omega is close to 1. It is cut off by this factor when J is reaching and exceeding an inverse of 1 minus omega. So it's very large. I think this is a quantum cutoff that we give to a quantum particle obtained by quantizing this wave function.
Right.
Yeah.
The unit does not line up when you
Which
consider it into the beta of 1 minus omega.
Why?
Beta has a unit 1 over energy.
Yeah, I'll explain to you. I set ADS box size to 1.
Oh, okay.
All the dimensional quantity are taking ratios of it and multiplied by ADS radius to make dimension.
Oh.
Yeah, so this is beta times ADS radius, and this is omega times ADS radius, if you're going to restore the box size.
So it's okay. So beta is large, but 1 over omega is small.
Beta in the radius ADS unit is order 1. In the ADS box unit is order 1. Omega in the ADS unit is close to 1. I think this is the step where we introduce the quantization of the classical waves and introduce this very large angular with a cutoff, the inverse scale of 1 minus omega. Without that, in classical physics, what I'm going to say from now on will be establishing slightly different story. Anyway, with this understanding that this mode with very large J will be dominating the thermodynamics of this gas, we consider the wave function of this gas at very large J, and this is actually found. It turns out that due to the very fast rotation of this gas, of this particle in this gravitational box, it will have a wave function supported at very large radial location in ADS. R, in terms of this rho coordinate that I introduced earlier, sorry for clumsiness here. R that I mentioned in the current slide was exponential of rho or something. And the reason why the wave function is peaked at large radius is quite obvious. It's obtained by a balance in the centrifugal barrier, depending on the angular momentum and the fixed gravitational attraction. So the larger the barrier is, the large becomes the radial stabilized position.
Is the red line where the specific heat changes sign?
Don't think there's a particular relation like that. Specific heat change sign in this region, but I mean, you have to consider two-dimensional susceptibility space, angular momentum, electric charge. You're questioning whether it's stable or unstable in some canonical way.
Yeah.
Yeah, we studied that. It was quite complicated. There was no obvious relation, as far as I remember. Yeah, yeah. It's obviously true that some susceptibility direction gets negative around this region. Yeah, yeah, but there's no sharp correlation. Yeah. So due to that reason, we basically consider everything in microcanonical ensemble, though I use sometimes the canon. Anyway, the wave function of this gas, which dominates thermodynamics, is very far away from the center of ADS, where the core black hole at omega close to 1 is supposed to be located. We're considering a black hole at finite beta and so on. It's a finite size object with radius of order 1 or ADS radius, while the gas is dominantly distributed at very, very large position. So motivated by this fact, we suggest a thermodynamic solution for the hairy black hole configuration, which is to boldly approximately superpose the core black hole and the ensemble of gas which carries large angular momentum, describing this omega equal to 1 physics. Okay? In equilibrium with each other at given temperature and given angular velocity. Okay? Luckily, I deviated well away from general relativity because we are suggesting a thermal configuration which explains more exotic black hole thermodynamics, but it's not a single solution of GR. It obviously has ensemble of matters outside the black holes explicitly included in our solution. So we suggest that this is a solution to the thermodynamic question of black holes. And I see that many GR people they're polite, so they don't really, but I could see from their face that, oh, this is not the solution that I wanted to solve. But anyway, we suggested as a solution for the thermodynamics, and there'll be some concrete evidence for that, as I explained to you. But there are some nice features, at least for the thermodynamics of black holes, if you accept this. It fills all the kinematically allowed regions in the charge space, which was above the equal to J line, because the solution we constructed has the structural form as follows. You start from a core black hole, which is no longer unstable at omega equal to 1. And on top of that, you're going to approximately add an ensemble or quantum gas of matters, which satisfies E equal to J. So the added matters have E and J equal to each other. So it goes up 45 degrees line to get to the total charge carried by the system. So if we scale this correctly, 0.2, 0.3, if we scale this correctly, this is a 45 degree line. So due to this, what do you call it, concave nature of this omega to 1 line curve, the curve black hole, going up 45 degrees line completely fills in this kinematically allowed region by our new hairy black hole configuration. In the blue region, it replaces the unstable core ADS black hole. It has large entropy and it doesn't seem to suffer from any instability issue. In the white region, it suggests a new solution where no black hole solution is there. Yes.
Would you indicate that the final solution is some sort of GR fluid, some fluid equation in GR?
To somehow coarse gradient and so on.
Well, that's a result of coarse gradient.
Yeah.
Like some fluid equation with some key.
Yeah, could be. Actually, maybe there's some works on this configuration. Yeah. One could be able to do that there, I think. Yeah. About the real original solution of solutions in classical GR, we at certain point I changed the problem to find a thermal configuration. But concerning the solution of finding the evolution of black hole with unstable modes condensed, we can just say that there won't be definitely, according to our picture, if it's correct, the picture I can say is that there will not be endpoint solution definitely. The solution will just keep evolving inside the explicit ensemble of these matters, and that will keep evolving without any stable endpoint. Okay? That's all we can expect. There's no proof of that, but that's it. I think it's moderately consistent with very elaborate and heavy numerical time evolution calculated by Chester. Yes, please.
In this kinematically allowed, so if you take the black hole solution and you continue with the parameters to this, what do you get? Does it become complex?
Start from where?
start from like one of the allowed black holes?
Yeah, the red lines, for example.
And like continue the parameters J or D into like that.
To here.
Widely. What is that solution?
Of following the solution space of curved black hole.
Yeah, what does it look like?
Well, it becomes unstable curved black hole until this point and disappear by being zero temperature black hole.
Like in the white region, it's like complex solution or something? Or?
Could be, but as a real Lorentzian solution, it disappears. It's a zero temperature extreme wave black hole function. Okay. So I'm comparing Harry solution and original curved black hole solution is the micro-Planck ensemble at fixed charge. So when both of them exist, we can thermodynamically let them compete. When only one exists, yeah. So if you could follow the curved black hole space, only the colored regions can be covered. Yeah, it's moderately consistent with the time evolution that has been done by Paul Chester. He introduced the perturbation to an unstable curved black hole and let it evolve a certain amount of time in which he can do some numerics. It's not very long time, but until he stopped his numerical evaluation, it didn't really settle down to definite solution. So it's really moderately consistent with what's known in the literature and so on. Yeah, that's what we suggest. I mean, it has some nice thermodynamic picture, and yeah, that's what we suggested. We'd like to make more concrete evidence that this one exists, at least in the thermodynamics of quantum gravity system. We made a few more consistency checks comparing the entropy of this configuration with other unstable Harry black hole solutions. Our configuration always win in the entropy sense, but I wanted to make more concrete tests. So if you don't know how to test after obtaining a solution, I mean, the usual strategy is to try to generalize the construction of solutions as general as possible and try to find some corners where quantitative calculation becomes here. So one could easily generalize this kind of constructions of Harry thermal configurations to include the charges on top of angular momentum. So we obtain some Harry configurations having mass, charge, and angular momentum. And in the three-dimensional space, ease the test and do some elaborate calculation easy, we could focus ourselves to a very special limit, okay, of black holes. And from this point, we consider black holes which can be realized in the superstring theory. And superstring theory has very strange symmetry called supersymmetry. One of the symmetries that superstring theories have. Super is for that symmetry. And you can have some special limit of black holes, charged and rotating, which preserves some part of this weird and funny symmetry that the superstring theory has. With this extra symmetry, we generally all know that if you have more symmetry, calculations become somewhat easier in many ways. But with this exotic symmetry, it's a really powerful symmetry which allows us to do various exact quantum computations. And I can take advantage of that to test or detect the existence of our claimed Harry black hole configuration, at least in thermodynamic sense. The way we'd like to test or detect this configuration is to compute the quantum entropy of the quantum mechanics describing this quantum gravity system, which is supposed to contain this Harry black hole configuration in this special symmetric sector. And this computation of quantum entropy can be done following the spirit of Andy and Kunlun that has been explored almost 30 years ago from now. We use the power of this symmetry to exactly compute the number of states carrying the definite number of charges, and you take the log of that, you compute the quantum mechanical entropy, and you compare it with the entropy of unhairy black holes and with hairy black holes, and see which one explains our exact quantum calculation more closely. This is the result. So I just briefly mentioned to you that, so we consider a very simple model, superstring theory, definite higher dimensional ADS 5 times 5. There's some reason why string theories prefer this kind of setup, but don't need to remember too much. It's admitting a holographic exact quantum description given by some supersymmetric, Yang-Mills-like theory with very large gauge group, SUN with very large n, number of groups are very large. Thankfully, with symmetry, we can do some computation. We do it at reasonably large n, number of gluon is n square 100, so it could be large. To exactly compute and plot the log, the entropies are these red dots. And I'm going to compare that with the Beckington entropy of the core black holes of the hairy ones and the area law of the unhairy black hole. Unhairy black hole entropies are given by this blue line. Hairy ones are orange line. Wherever two of them coexist, the hairy one has larger entropy by construction. Okay, so I plot the entropy as a function of an angular momentum, fixing all the charges, other charges, fix that definite value. So considering that it's not a real large n calculation and it's not a very large charge calculation, I think this is quite semi-quantitatively showing that this region, the entropy is faithfully explained by hairy black hole. Most of the region is actually where the unhairy black holes don't exist. So I think the quantum calculation exactly semi-quantitatively supports the existence of this solution, at least as a thermodynamic one.
This black hole, is it expected to be supersymmetric?
Yes, we are considering a supersymmetric limit of the solutions we have constructed. Yes.
But I thought it necessarily had like a thermal ensemble of gas outside.
Yeah, it's a kind of odd. Yeah. So you construct these hairy black holes and you take a zero temperature limit of that. In this supersymmetric theories, there are lots of matter states which are preserving this supersymmetry at zero temperature. But still you add any, I don't know what that's like equilibrium, but with the core supersymmetric black hole and the matters, all the other chemical potential which are non-zero are matching in sort of equilibrium. Yeah. So that's the nature of this so-called thermodynamic configuration. Everything at zero Hawking temperature.
I was wondering if you keep correlation functions in this very background, if they decay like power laws or like exponential
In what?
in time. Like a black hole without hair would decay like an exponential.
Yeah.
Now you have this hair near the boundary, so you could scatter off that and then have power.
By the hair. I think even without the hair, if you consider this very special supersymmetric black holes and so on, there are some results that the decay is okay. So I don't know. I don't know in time. Yeah.
In the extreme limit, yeah, indeed it is.
Is this a classical computation or?
Oh, this entry is a quantum. We count integers, quantum states. Yeah.
But then the idea in the classical one that this is some sort of chaotic configuration of classical waves banging around between black hole and bucket.
You mean this hairy?
Yeah.
Yeah.
So I guess can you write down like is that like you can write down like a supersymmetric solution of the like Einstein equation?
Even in the supersymmetry limit, it's not. It's the black hole side is a core black hole solution representing an ensemble, we believe. The hair part is explicitly an ensemble. Yeah, so it's very far from classical solution. Yes.
Even in the temperature goes to zero.
Right, because there are so many supersymmetric gravitons and photons hanging around in black holes. Yeah. And yet,
You compared the entropy you're comparing is the core black hole entropy.
yes.
Should there be some contribution to the entropy from the hair?
Yes, there are some, but it's subdominant in this large n and semi-classical limit. You can estimate that. I think the black hole entropy is inversely proportional to Newton constant. Hair contribution is inversely proportional to square root of Newton constant or something. So it's always subdominant. Yes. Okay. I finished half of the talk, but I think I need this glass. Say a few words and I can close. I mean, are the slides up? Or
Yeah, the slides are still up. Yeah, everything.
I mean, will it be after the
the talk is being recorded and will be posted on YouTube.
Oh, so only the part I show on this talk will be.
Yeah, unfortunately, I don't know if we can make.
Okay, I'll
so,
just slowly change between the slides, so I will leave a record.
we have like 5 minutes left.
Okay, okay. I will try to wrap it up. Wrap it up. Yeah, I fragmented into 2 or 3 steps. So okay. So I just all I wanted to comment on about the last computation is, you know, I used the quantum computation with really long history. I mean, quantum entropy calculation for black holes. And that has been very important question for the past 3 decades to unravel lots of mysteries about quantum black holes and quantum gravity itself. And I used all these just to test the existence of our suggestion, because we are so urgent that those people, especially the classical GR people were really, I can understand because I was not solving their problem. So we used all this machinery to test the validity of our suggested solution. But during this calculation, we have shown quite a lot of things, right? We have counted the number of states, at least the supersymmetric ones, very special ones, which account for the novel entropy of these hairy black hole solutions. And this is part of a bigger program of trying to understand the innards of the black hole, the microstate structures, and so on. And once you have computed the entropy of a large set of states, you can next, of course, ask, how do these black hole states look like? Okay? That's always been an important question. Okay? And these are supposed to be very heavy states, because the black holes are very heavy, opposed to light states like gravitons and photons and so on. So I was supposing to switch a gear from this point and explaining some more quantum things. And the thing is that things become a little bit more technical because we only know how to do it in very simple models. So this supersymmetric sector, the black hole entropy was accounted. And there has been developed a way of characterizing these heavy states themselves, which account for the black hole entropy that I've just shown you in the previous slide. So we can count the states easily first, but characterizing and studying the states themselves are quite different. I wanted to explain a way of how to characterize the no-hair theorem and hairy black hole states at the level of each microstate in these special supersymmetric models. Understanding the structure of all black hole microstates. There are a huge number of states, so it's very difficult. But after recent studies in the past few years, the structure of the hairy black hole states and the disallowed hairs, the no-hair theory, most that satisfy no-hair theory, can be easily distinguished by a particular quantum suggestion. So let me just try to bravely go through only the essence without explaining too much detail. I don't really want to go over time. Let me just explain this part. So we see a pattern of that. So I can go 2 minutes or so.
Yeah, sure, that's fine.
Okay. Explain this slide and just show. So if you try to re-understand the patterns of hairs that appeared in the construction of our new hairy black hole solutions, especially let us consider that in the symmetric sector, the supersymmetric sector, so on. So if you have a core black hole which is rotating and charged, you want to first have a probe particle picture of these black hole hairs instead of wave functions. Impose these symmetry conditions and so on, it's supposed to have a circular orbit at definite radius. Okay. So it's a classical representation of the hair. It should have an angular momentum larger than a critical value for its orbit to stay outside the horizon. Because again, the orbit is determined by balancing the centrifugal barrier and the gravitational attraction and so on. So it only exists outside the event horizon with angular momentum of the hair larger than a critical value set by the horizon size of these black holes. And a similar kind of conclusion can be made in the wave picture, although there's a little bit of certainty of studying perturbations of zero temperature black holes and so on. More or less similar conclusion can be obtained, so if you can trust me. So the upshot is that the symmetric hairs exist when the angular momentum is larger than critical value. If it's smaller than this critical value, there's no hair. Such mode is swallowed by black hole instead of existing outside the black horizon. And the critical angular momentum is when the orbit is on the black horizon. What has been found in this quantum field theory, quantum mechanical calculation of heavy states and light states, or heavy operator or light operator, the creation operator for this mode, it's very something similar. Okay? If you consider a heavy state that we have understood and try to multiply a light particle mode to it, the product remains to be a non-trivial state when the angular momentum of the light mode is larger than sufficiently large. If you consider multiplying an operator which has small or no angular momentum, they turn out to be trivial in this supersymmetric sector of this Hilbert space. We have developed that in a precise formulation. If it's written as a symmetry transformation of something, it's trivial in this supersymmetric sector. I mean, I haven't developed anything precise. So this is one of the heavy operator that we have recently computed in this SU2 toy model. This is the simplest of the light operator, which doesn't carry any angular momentum. So abusing the classical picture, it should be sitting inside the black hole. If you multiply them after elaborate quantum mechanics calculation using 2x2 matrices and so on, you indeed can see that it's trivial, sort of consistent with the gravitational picture and so on. And that seems to be leading to characterization of the hairs which are allowed with large angular momentum and which are not allowed in this symmetric sector, which I think is interesting and would have some possibly some far-reaching implications. So I think here, let's say more about the generalities of this characterization. I won't say anything, but it will be recorded, right?
Yeah.
I won't say about this. Relation to some possible relation to some information paradox, to predict two-point function, no-hair theorem. And this is a problem that I just began to think about, which I would like to comment on, but I just read the legal record here. And then we conclude. Because I spent so much time, I'll just conclude with concluding remarks. Shown. Thank you very much.
I think we're at time unless there's like some super quick question. If not, let's thank Seok again. I think there's lunch outside.